times 1 over root 2 and 1 over root 2, the result will be 0. Now I got the directional derivative. So once more, the directional derivative at the time being, here is the gradient vector at 1, 0, 0, 0. Then multiplying by v, since the gradient vector is null, then the result of the directed derivative in this direction is going to be null also. So this is how to evaluate. As you can see, this problem covered two main things. Covered or tested the knowledge, your knowledge in the continuity, and also your knowledge in the directional derivative, as you can see. For this problem in specific, we should study differentiability. If I want to study. So this function is continuous. Remark, I must say that. This function is continuous. We saw that it's continuous. And the directional derivative is equal to 0. Now I need to discuss the differentiability. It's not required, but I will do it in order to complete the picture. Okay? I will do it. I need to discuss the differentiability of this function at the point 1 and 0. For this function to be differentiable, if you remember, then the remainder should equal to 0. The remainder, what I'm going to test? I'm going to test this limit of h and k tends to 0 and 0 of f a plus h b plus k minus the value of the function times h, the value of the function times k divided by the norm. To be differentiable, this relation should equal to 0. This limit should equal to 0. If it doesn't exist, if this limit doesn't exist, or it is exist, but it's not equal to 0, then your function is not differentiable. So once more, all I have to do is to make the substitution in this law, as you know. So all I have to do is to start substituting around the point that I'm testing. The point I'm testing is 1 and 0. So this guy is equal to 1, and that guy is equal to 0. 1, 0, 1, 0, and 1 and 0, and start substituting in the main function and in the partial derivatives that I have. The partial derivatives, if you remember, are zeros from the beginning, okay, from the previous slides. And the value of the function also at h plus k, when h plus k tends to 0, is going to conclude. So once more, f at 1 and 0 is equal to 0. The partial derivative at 1 and 0 is equal to 0. The partial derivative is equal to 0, which means f1 plus hk divided by h squared, k squared, is equal to 0 or not. So instead of dealing with all of this problem, or for those guys, all of this is equal to 0. I'm dealing with this part only. Which means 1 plus h and the k. And this is the value of the function. So I will bring this guy, replacing y by k and the x by 1 plus h, and also do the substitution. This is going to be the function that I'm dealing with after substitution. Okay? Now I will need to search for the limit of 3kh divided by h squared plus k squared. Okay, I can do by the beginning the directed method using h0, h tends to 0, or if h is equal to 0, I will discuss the limit. K is equal to 0, discuss the limit, and also I can discuss when h is equal to k. If you discuss when k is equal to h, this is going to be 3k squared over 2k squared, which means the value is 3 over 2. Am I right? It's not equal to 0, so the limit is not equal to 0. The limit is supposed to 3 over 2. Another remark. If I'm using the line k equal to negative h, the value is going to be negative 3 over 2. Okay? So this limit doesn't exist. Once the limit doesn't exist, it means that this function is not differentiable. So remark, for this problem, remark the following. The limit doesn't exist. Or even if it is exist but not equal to 0, it's the same result. The function is not differentiable. Let's look to this problem from the beginning. Okay? We have tried to solve this problem. We discovered that the partial derivatives exist. Yes, and both of them equal to 0. The function is continuous, proven from the beginning. and the function is not differentiable, which is a confirmation on the previous theorem that we had in the previous session, that the existence of partial derivatives doesn't guarantee that the function is differentiable at a point. So once more, because it may come to you as a true or false, or choosing the correct answer, once more. If the partial derivatives exist, it's not a guarantee that the function is differentiable at this point. Like this problem. It is continuous, partial derivatives exist, but it's not differentiable. Okay? So once more, this means, first of all, f is not differentiable. Although f is continuous and the partial derivatives at 1 and 0 already exist. Okay, both of them are zeros. That's a very nice problem by the way. This is why I solved it. He was asking about the continuity and the directional derivative, and this is why I continue also to differentiability in order to compare them together. That's another problem. You should study the continuity, compute the partial derivatives, consider the vector, study the directional derivative, same steps exactly, but we changed the kernel of the function to be 3x squared, and we are testing around 0 and 0. Same steps exactly. Study the continuity. I will change to polar coordinates, r cosine theta, r sin theta, which is much easier to do. Once you do this, this is going to be the substitution. It's going to be 3 cosine squared sine r sin theta, which is going to equal r tends to 0. The value is going to be equal to 0, so the function is equal to 0. The limit, if you remark, the limit of the function is equal to the definition, so it is continuous. Once more, as I told you, it is continuous. How to compute the partial derivatives? I will use the law, which is f of h and the 0 minus f double 0 over h, and then f of 0 h in the y direction minus f double 0. That's the law differentiation in the direction of x, and the result is equal to 0. And if I want to use the partial derivative with respect to y, the only difference here, this is going to be 0, that's going to be h minus f double 0, as you can see. The result is equal to, so the partial derivatives exist, it's equal to 0, the gradient vector is equal to 0. Once you multiply it by v, it's going to equal to 0 also, so the gradient vector really exists. In this problem in specific, I used the definition that I told you about at the beginning for the direction in the many slides, in the directional derivative. And once you try to use your vector with the limit as from the definition, let's see if I make the substitution, okay, of the d of 0 and 0 and start substituting. Okay, just a little second. These are the values. I'm trying to evaluate the value. Then the result will be 6 over 5 times root 5 for this function. Remark that in directional derivative, I want to remind you about this. For directional derivatives, for d, v at f, it's equal to the gradient vector of f times the vector. This is applicable when the f is differentiable. But if your function is a piecewise function, you are not sure about the differentiability, even if the function is continuous, like the previous problem. So I will use the definition of the directional derivative. The definition of the directional derivative, it is this law. That's the law that I'm going to use, which is f of x naught plus h times a, y naught plus h times b, minus the value of the function, and divided by h limit h tends to 0. And I will start substituting in the given kernel of my function by this relation. And as you can see in this problem, if I'm using this value, the directional derivative will equal to 0. But in this case, I will have to use this law in order to find the directional derivative of my function. Once more, this is for the differentiability of f of x and y, if I want to discuss it. When r is equal to 0, so this doesn't tend to 0 as r tends to 0, so this function is not differentiable, exactly like the previous one. This is why I had to evaluate the directed derivative from the law that you saw previously. معايا see that? Okay. So in this case, f is continuous at all points, but it's not differentiable. This is why I will have to use the differential. In this part also, okay, or in this bunch of slides, there is nothing new, okay? All of them are continuation for solving more problems from the sheet. As you can see, this is why I've shared all of this with you, because I don't want to be delayed from listening, as you know. Okay, so once more, there's nothing new. You want to consider the function phi defined in R except 0. So your domain for definition it's R except 0 by the expression phi of x equal to x, the norm of x to the power of 2 minus n. Justify that phi is differential at all points in its domain. Determine the partial derivatives of phi at the point 1, 0, and the derivative of phi at the same point in the direction of an arbitrary unit vector, any arbitrary unit vector. Once more, don't get scared. Don't be scared. Here he is giving you the norm of this vector. What's the norm once more? It is the square root, صح? Of the square of the components. Since we are talking about n is greater than 0, then it's gonna be the square root of x1 to the power of 2 plus x2 to the power of 2 plus blah 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 plus x sub n to the power of 2. Am I right? It's an open one. Okay, so once more, phi is gonna be the square roots that we talk about, which means the power will be divided by 2. That's the power. And it is a sum of squares. So it's from 1 up to n. So instead of writing, it is the square root of x1 to the power of 2, x2 to the power of 2, blah, 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 xn to the power of 2. All of them to the power of 2 minus n, I can use this short written form. معايا say that? They are exactly the same, of course. صح? Okay. For x belongs to Rn except 0, so you are safe here from the existence of the origin. Now, if I want to find the differentiability, all I have to do is to differentiate this guy, and it will be differentiable since we already moved, we excluded 0 from our derivative. So if I want to get the derivative of this function, this is a smooth function. This is the sum of squares. So it's a x1 to the power of 2, x2 to the power of 2, x3 to the power of 2. You have no problem with it. The only problem that may happen because of the existence of 1 over 2. The power is 2 minus n over 2. This is the only obstacle. And this will result in a division over 0. But you already excluded 0 from your domain, so you are in a very good shape. So once more, if I try out raising the power to 2 minus n over 2, okay, the only exception is at 0, which is outside our range, so there is no problem. If I want to differentiate this function, let's look how to differentiate and how the differentiation is really very easy in this case. If I want to differentiate, then the derivative, of course, if I want to make a change of variables using r equal to the square root of all of this, I will get rid of the 1 over 2. So it's going to be r to the power of 2, 2 minus n over 2, which means r to the power of 2 minus n. And that's the derivative. If I want to differentiate, the power will go down times, and I will take 1 from the power, then differentiating r squared, which is a function in x1, x2, xn. So if I'm differentiating with respect to xi, the only part that will affect in R2 is the part containing xi. صح؟ معايا see that? No. Once more. But see, once more. I can differentiate this function. I can differentiate this function. Let's differentiate it together. If I want to differentiate, the power will go down. 2 minus 2 minus n over 2. صح? For the sum of x squared j from j equal 1 up to n to the power of 2 minus n over 2 minus 1. Am I right? That's the derivative of the power. Then I will try to differentiate what's inside. What's inside will be differentiating. If I'm differentiating with respect to xi, then the only part that will get affected from what's inside is the part with xi. Do you read me? The other values of x is going to equal to 0, because this summation is x1 to the power of 2 plus x2 to the power of 2, blah blah blah, plus xi to the power of 2, blah blah blah, plus up to xn to the power of 2. So once you make your partial derivative with respect to xi, the only part that will work is this one, 2 over xi. While this guy is going to equal to 0, this is going to equal to 0, this is going to equal to 0. صح؟ This is why I thought if we change into R, it's going to be easier on you to imagine this case. So once more, if I made the change of R, you know that R is equal to the root of x1 to the power of 2, x to the power of 2, x3 to the power of 2, blah, 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 up to xn to the power of 2. So if I make this substitution, it will make your life easier. Am I right? So once more, this is R squared, which is going to be a replacement of the summation. Differentiating, the power will go down. I will subtract 1 from the power, then derivative of R, but just only with respect to xi. Now I will have 2 minus n, just only 2 minus n, because differentiating R squared, it's a 2 of, it's an x to the power of 2. So xi to the power of 2, once you differentiate, it's going to be 2. The 2 will eat this 2, so they will eat each other. And you will have xi only. Are you with me? No.
I just don't get why the r squared is going to be x to the power.
Okay. What's R squared? صح؟ Zero. صح? 0, 0, 0. What's the part that's going to be differentiated? The rest are going to be. So this is why I'm replacing this part by 2xi. The 2 will eat the 2. Do you read me? So your function will be this way. ها تمام؟ Okay. Okay, so that's the partial derivative. Okay, at the point 1 and all of these zeros, R squared is going to equal to 1 once you make substitution. So for I is equal to 1, now partial phi, partial x1 is going to be 2 minus n to the power of 1 negative n over 2 times 1, which is 2 minus n. So the vector at this case, for my case, it's going to be exactly, that's the gradient vector. It's going to be 2 minus n, and all of them are equal to zeros. This is the only one that will appear with me. Now I have the gradient vector. I have the vector v, which is a generic vector he gave to me. So multiplying them together with 1, 0, 0, 0, 0, the only components in the first one, 1 times 2 minus n, times v1, which is the first component only. This is the directional derivative of this function. Also, you have another problem which contains r sine theta cosine, r sine phi cosine theta, rho sine phi sine theta. Do you remember that's the spherical coordinates? Am I right? And he wants you to determine the Jacobian matrix of the function t at the point given. Compute the determinant of the matrix obtained in the previous item. It's really very simple. This is rho, theta, and the phi. Those are the 3 components. If I want to get the Jacobian, The Jacobian usually used with the functions, the vector valued functions. Do you remember what the vector valued functions? The functions which has several inputs and several outputs. I have several inputs which are r, theta, and phi. And several outputs. What are the several outputs? R sine phi cosine theta, F1. R sine phi sine theta, F2. And then R cosine phi, F3. So the Jacobian will be differentiate the first with respect to rho. The first row will be derivative of this guy with respect to rho, with respect to phi, with respect to theta. The second row will be differentiating the second function with respect to rho, with respect to phi, with respect to theta. The third one will be differentiating rho cosine phi with the three variables with respect to rho, with respect to phi, with respect to theta. That's the Jacobian matrix. Here we go. X stands for the first component. So that's X. This is Y. And that's Z. So I'm differentiating the first component, but with respect to rho, theta, and phi. Here we go. Partial X, partial rho, partial X, partial theta, partial X, partial phi. Do the same with the second component and the same with the third component. Those are the derivatives. As you can see, I want to evaluate them at 2 pi over 3 pi over 4. So all I have to do is to substitute, as you can see, and gathering them together in the Jacobian at that point. معايا بس say that? It's a direct substitution, as you can see. So that's the determinant. Of course, that's the Jacobian, and evaluate the determinant of this function is not going to be hard to evaluate. The determinant will equal to rho square sine phi, and so it's going to be 2 root 2. Okay? So also, that's a new information for me. Instead of evaluating all of this, I can directly, if I'm in spherical coordinates, the determinant of the Jacobian of spherical coordinates is rho square sine phi, which will make your life much easier than trying to evaluate this value. Okay? So I want you to remember this guy. Now I have the relation, the Jacobian matrix. Also another problem with the same. Here is giving you bxy, the Cartesian coordinates, in a space of RTCZ, which is the cylindrical coordinates. Consider the function g of r, theta, and z, and equal to x, y, and z. Determine the Jacobian matrix of the function g at generic point rt theta. Find its determinant. Then consider the function u, knowing that f sub x at 2 is giving you the first derivative with respect to x at the point, the first derivative with respect to y at the point, and he wants you to determine partial u, partial r, partial u, partial theta at the point 1 pi over 4 and 0. It's all direct relations, and he wants you to define the abbreviated section, write partial 2u, partial r theta, and partial 2u, partial r squared in the partial derivatives. So I will start with the relation in the cylindrical coordinates, that x is equal to r cosine theta, y equal to r sine theta, and z is equal to z. Once more, it's a link between the new parts and the previous ones. As I told you, we are not going to, they are tools with us. So the Jacobian matrix now, I will differentiate the first component with respect to r, with respect to theta, with respect to z. Second component with respect to r, with respect to theta, with respect to z. The last one with respect to theta, with r to theta and z. Those are the derivatives. That's the substitution of the Jacobian. Try to get the determinant. The determinant in this case is going to be easier. It's going to be very simple because you can expand this determinant, but using the element on the third row and third column, which is 1. Okay, so I can evaluate it, which is going to be r. Find the partial u, partial r, and the partial u, partial theta at 1 by 5 at the indicated point. This is u, f of x, y, and z. Use the chain theory. U is f of x, y, r cosine theta, r sine theta. So dx, partial x, partial r is going to be cosine theta, partial x, partial theta, negative r sine theta. This is partial y, partial r, partial y, partial theta. They are already identified. All I have to do, in order to get partial u, partial r, I will differentiate the function with respect to x variables, but multiplying by partial x, partial r, partial y, partial r, partial z, partial r. This is how to get the partial derivative in the case of composite functions. Because I'm connecting x, y, and z and r and theta. Direct substitution, of course, you will get the value of your function, which is negative f of x for the derivative with respect to r or with the derivative with respect to theta. Those are the results that we had in the previous session. Now I will make the substitution for r at 1 and theta pi over 4 and z is equal to 0 according to the evaluation point. I have the values with me, so I can get the value of x and the value of f of y. Now partial u, partial r is evaluated, and same way like partial u, partial theta is evaluated. I am done with part number B. For part number C, I will do an extra derivative with the composite function that I have, f of x, r, and theta, y as a function r and theta, and z in zeta. So it's a generalization of your function using the partial derivative, as you can see. This is the second derivative. This is also another problem from the problems that we have previously. Just remember this part about the partial derivatives for composite functions. Okay. This is very, very simple. If you will be very lucky if he asked you about something like this. He wants you to begin being phi such that from r to r differentiable function z is y squared over 2, and the phi is a function in y over x plus log y. He wants you to show this. All I have to do, say that, is to get partial z, partial y. I will differentiate this function, partial z, partial y. Then I will differentiate this function, partial z, partial x. I will substitute in this part, and the result will be simplified to y squared. Do you read me? So it's very, very simple. This is the first derivative with respect to y. So once you try to make a derivative with respect to y, this is going to be differentiated, 2y over 2, which is y. Once you try to differentiate, it's going to be phi dash this function times the derivative of this part. Log y is going to be 1 over y. As you can hear, also I want to grab your attention that log y in this slides, it's ln y. Log y, you will treat it as ln y. Okay. So it's going to be 1 over y. This is why you can see 1 over y. Do the same, partial z, partial x. Start differentiating with respect to x. So this is going to equal to 0. This is going to be phi dash. Then times. Differentiate with respect to x is going to be negative 1 over x squared. This is the value. Take these two quantities and multiply them on the left hand side and simplify. This is what I'm doing. Left hand side, multiplying, substituting. Just simplifying a little bit, you will find it's equal to y squared. All of these problems are exactly the same. This is exactly the same. This is the function. Differentiate twice with respect to t. Then differentiate twice with respect to x. Multiply the derivative in x with respect to c squared, you will find them equal to each other. This is also exactly the same way like. So it's a repetition of the same idea. Actually, you will take this in mathematical analysis too, and those are partial differential equations. That's the wave equation, as you will see down the road. This is one of the partial differential equations. Also, you will see down the road. Okay? It's very, very simple. In problem number 16, he is giving you partial u, partial x, partial u, partial y. Consider the function defined by phi of r and theta as outlined. Determine partial phi, partial theta, partial phi, partial theta at the points 2 and pi over 3. So mainly find the partial derivative, then substitute. It's a direct substitution, of course. That's a composite function. This is why partial phi, partial theta, it's a partial, I will differentiate the function with respect to u, then multiply by partial x, partial theta, partial y, partial theta, and I will use the direct substitution. So this part, partial y, partial theta, okay, I will grab it from its component. Here we go. Here is x equal to r cosine theta, y is equal to r sine theta plus r. So all I'm doing at the time being is just trying to find partial y, partial theta, which is going to be r cosine theta, then partial x, partial theta, which is going to be negative r sine theta. Those are my derivatives. Then start substituting in this one, partial u, partial x, as you can see. From partial u, partial x, it's going to be e to the power of x cubed negative r sine theta, 3yr cosine theta from the given function that we will have. Then partial phi, partial theta is going to be e to the power, I'm using the substitution that I have. And same way like for the y component, it is proven. Also, for another problem with the similar issue 17 and 18, I've shared all this part with you in order to make things easier. It's going to be exactly the same. This problem is also, they are going to be the same. I've shared this with you. I want to solve on this problem, it is the last problem in the sheet, which is about the approximation of a function. In order to approximate a value of a function using the derivative, I will use this equation. Already we had it previously in the, this is really very important. This is the approximating the equation of a function, okay, of a function in the neighborhood of x node, y node. If you remark, this is gonna be the gradient vector of f at x node, y node, times the position vector x minus x node, y minus y node. This is why you can find the partial derivative of f at x node, y node times x minus x node, and of course this is the dot multiplication. You will find the partial derivative of f with respect to y times y minus y node. That's the approximation that I'm going to use. If you remember the approximation formula, it's a direct substitution. You will do nothing, just a direct substitution. So I need to find, let's go through together Ms. Sena. I need to find the value at 0.07 and 0.4. And that's the function that we are going to use. So all I have to do is to choose the values of x node, y node. Okay? So once more, this is f sub x. I'm going to get the first partial derivative. The first partial derivative of f of x at the indicated point. This is going to be simplified as much as possible. So f of x, as you can see, f sub y, same way like, and I will try to simplify it as much as possible. This is f of y. Then I will get f at 0.07, 0.04, f sub x at 0.07 and 0.4, this is x, that's y, and the f sub y, this relation, replacing x by 0.27 and xy is going to be 0.27 times 0.04. So I have their values. Now direct substitution. This is going to be the value at the indicated point, and this is going to be the values of x minus 0.7 plus the function times y minus 0.24. At the time being, I can find, this is the approximating polynomial. I can use it to find the value of f at 0.075 or at 0.0399. I can use this polynomial in order to find the values of these values just by replacing x and y by these values. This is also a very important remark. Usually it comes in exams, but the problem is to remember the approximating equation. This is the approximating equation that I want you to remember, and we already have it in the previous slides. Okay, that's the part of the tangent plan. If you remember the steps of the tangent plan, I did go through today. First of all, get the gradient vector, substitute by the point, you will have normal vector, then multiply the gradient vector times the position vector, x minus x node, y minus y node, z minus z node, equal to 0. It's enough one problem on them. I will solve the problem number B. okay, as a training. So all I have to do is to get the gradient vector, just to remind you. Those are the 3 steps: recognize the surface, compute the gradient vector, use the point and the normal form. So this is the function, get gradient vector. How to get the gradient vector? Differentiate with respect to x, differentiate with respect to y, differentiate with respect to z. That's the gradient vector, which is gonna be simply 2 over x, 2 over y, 2 over z. Then I will substitute by the point, which is 0, 0, and 1. Now I have a normal vector. After doing this, I will, by 1 over root 3, 1 over root 3, and 1 over root 3. Make the substitution, okay? Now I have the normal vector. In order to get the tangent plane, it's gonna be 2 over root 3, 2 over root 3, 2 over root 3. And all of this will be dot product the position vector. X minus 1 over root 3. Y minus 1 over root 3. Z minus 1 over root 3. And equal to 0. I am see that. This is the equation of the tangent plane, as you will see. So once more, that's the gradient vector, as I told you. Substituting by the point, this is the normal vector, multiplying by the x node, y node, z node. So all I have to do is to multiply a times x minus x node, b y minus y node, c times z minus z node, where x node, y node, z node are the coordinates of the point. And the a, b, c are the coordinates of the gradient vector. Now you have your tangent plane. So this part is important, and the importance of this problems, it's really simple. Okay. Now once more to the implicit function. That's a quick reminder, because we did go through at the beginning of our work today, that if you need to find an implicit function, all you have to check is that the function value at x and y is equal to 0, and the partial derivative